Um, let's get going, everyone. With today's virtual TEOS seminar, which I'm kind of glad it was virtual. There was probably no way Marv was going to be able to make it, given the weather the last couple of days and so forth. But anyhow, it's my pleasure to introduce Dr. Marv Geller, who's a professor emeritus here at SoMAS. And he's been affiliated with Stony Brook for decades and so forth. So I want to go back here a little bit in the history. I'll just go sort of chronologically here, where Marv was a professor and director of the Institute for Terrestrial and Planetary Atmospheres. Back then it was ITPA, and back then it was also called Marine Sciences Research Center. So he was basically the professor and director of ITPA from 1989 to 2002. And then from 1998 to 2003, he was actually the dean of MSRC, now called SoMAS. So the dean and director of MSRC. And so I remember those days because I came into MSRC, I think around 1999. And I actually remember the day Marv called me and offered me the job. That was a very happy day. So that goes way back. So Subsequently, he's been since becoming dean, and after 2003, he was professor to 2015, and then since 2015, he's been a professor emeritus. A little bit more history of Marv. Before Stony Brook, he was assistant and then promoted up to full professor at the University of Illinois and also at University of Miami. And then the other a big thing with Marv is that he actually worked with NASA in the 1980s, including serving as the chief of the laboratory for atmospheres at NASA Goddard in the late 1980s. And then he eventually from NASA came to Stony Brook. So I went sort of maybe in a confusing order. But anyhow, Marv is a fellow of the AMS, American Meteorological Society, and AGU. He was awarded the NASA's Distinguished Public Service Medal and also COSPAR's International Cooperation Medal and a SCO STEPS Distinguished Service Medal. And he has hundreds of publications dealing with his research. And today he's going to talk about some of his work here on research on atmospheric turbulence in recent years. And I think we figured out the technical things. So, Marv, I think I'm going to turn it over to you. Thank you.
Okay. So I seeing Brian reminds me of that one. I was a little unorthodox in all my administrative positions. Like, I don't know, Brian might remember this. I was out of town when Brian actually visited Stony Brook the first time. So actually the interview for him, I believe, took place in a bar in Seattle where I had given him a call. So, you do what you do. Anyhow, I'm not such a young guy. So recently I've been doing work on atmospheric turbulence. And basically, what I've been using is high resolution radiosonde data. This is the abbreviation which I'll be using, high vertical resolution radiosonde data, to get information on gravity waves and turbulence. And this talk concerns my research that using this data since I retired. Let's see if I can get rid of all this stuff. No. Yeah, let's see if I can, so I can see my own slides. Okay. Um, oops. Now I can't. Let's see. So now I can't. Oh, there we go. Okay. So let me show you what I'm talking about. All meteorologists are used to using radiosonde data, but you're probably used to using the mandatory and significant levels. Actually, nowadays, when it went to GPS, you get data every 1 second, but you don't see that data. It's culled down quite a bit. Historically, it's because of limited communication, but that's no longer a problem. But there's two types of data. There's the raw data and there's the process data. And if you look, one of the differences between the raw and the process data is that there's a radiation correction in the process data. And so if you add the this radiation correction over this height interval, 17 to 18 kilometers, you'll see that they pretty much lie on top of one another over this region. Except if you look a little more closely, you'll see that the raw data, the black line, is more small scale features. So there's some inherent smoothing that went into, besides the radiation correction, there's some inherent smoothing. So if you try to find out what the smoothing is, it's interesting because the Sterling support people would tell you that the nature of the smoothing is proprietary to the instrument manufacturer. Well, that's a problem if you're going to be using this high resolution data. So we sort of, in this JTech paper last year, Wang and Geller, Ling Wang was a PhD student in, I think, 2003 at SoMAS. We tried to figure out what the smoothing is and the type of smoothing and some of the features of this. Now, the availability of high resolution radiosonde data has evolved tremendously. The field sort of got going in 1995, a paper by Allen and Vincent in JGR, and it analyzed the data over Australia. And then Wang and myself, for his PhD thesis, we used the US data. So it include continental Alaska, um, Pacific, a little bit of Caribbean. But just recently, all this data has become available. If you look down here, the high resolution radiosonde data, there's hundreds of data. So suddenly this high resolution data becomes available for research purposes. And one of the research purposes is to look at turbulence and gravity waves. But I want to make the point that the availability has grown tremendously over the last, well, 20 years. So what we did, looking at the smoothing, is we take a delta Z. In this case, the delta Z is 500 meters. The reason we chose 500 meters is you could see what's going on. So here's a segment sounding 22 to 24 kilometers, and it's at San Juan, Puerto Rico, but that's irrelevant, really. And so you see the black curve is the raw, it's a little noisier. The red curve is the process data. And then we can put these second order spline fits over segments. And so we chose the 500 meters so you could visualize it. If we chose 100, it would be very noisy and so we chose 500, although we don't use that much. And so then from the spline fits, the various spline fits, we can then look at the departures, and then we can find the root mean square departures from the spline fit, and that would characterize either a mixture of the geophysical information and the noise in the sounding. So I hope I made that clear. And a few other things here would be, for instance, if you look at the RMS, let's see, I'm trying to think which is which, but these curves show the RMS in the different the raw and the data. I think this. So here would be the RMS. I think in the processed here would be the raw. So the show more noise in the raw, and this would be the ratio, which is less than 100, basically, less than 1. So there's less noise in the process data than in the raw data. I hope I made that clear. So using these radiosondes, we look at segments. 5 to 15 kilometers, we characterize a troposphere, and 15 to 25 kilometers would characterize the lower stratosphere. And if we look at the RMS from what I just described, but here the RMS is for delta Z 100 meters. So we're looking at quite small scale features, the fluctuations that are less than 100 meters. So the spline is over 100 meters in this case. And so you see an interesting situation here. You see, first of all, if you look at the color scale, if you look at the color scale, I hope, if you look at the color scale, why is it wondering this? If you look at the color scale, you'll see that the raw data color scale is twice as much at 26 versus the 12.4 than the process data. So there's more RMS, there's more noise in the raw data than the process data. We could see that, it just quantifies it. But the other thing you see is this kind of an interesting geographical pattern. And this would just be the troposphere, this would be the other one would be the lower stratosphere. And it's more obvious in the lower stratosphere. The RMS values in the lower stratosphere, and this is, by the way, this is at 00 universal time. So, and then there's January left and July right in both of these. I should have pointed that out earlier.
So Marv, you may want to point out the color scales are different between raw
Yes,
and process.
right. That's why I was pointing out that there's more noise in the raw
Mhm.
data because the color scale is twice as large.
Yeah, yeah.
Yeah. So, but if you look at the lower stratosphere, now you see an interesting pattern where you have biggest RMS data here, biggest RMS fluctuations here, and here you see it sort of fills up more of the continental US. This is January and July. So you see this narrow sliver in January, and it fills the western portion of the continental US in July. And again, you see in this lower stratosphere the same thing that Minghua just pointed out. Here it's more than twice as much in the raw data than in the process data. And also it's more in the stratosphere than it is in the troposphere, the fluctuations. Okay? I hope that's clear. So what's going on? So what's going on is if we looked at the day-night pattern at 00Z, at 00 U time, UCC in January, we see the sunlit portion of the US is this far western portion, but in July, the entire part of the US is under sunlight. So by this picture, I think you can see that we would associate large RMS values with sunlight. So there's a day-night difference in the small scale RMS. And we hypothesize, and this is something that should be followed up, we hypothesize, I already showed you the radiation corrections that are applied to radiosondes, but that's applied over the segments of the soundings. But as the radiosonde goes up and down, it goes up, the instrument is swinging, it's rotating, and so it's experiencing different sunlight falling on the instrument rather rapidly. And we believe that that's what's causing the greater small scale temperature fluctuations under sunlit conditions and under nighttime conditions. And we propose later a way to actually verify this, but I'll get into this a little bit later. So, okay, the moral is, particularly in the lower stratosphere, there's much more small scale temperature fluctuations that we attribute to noise in the daytime than nighttime. The other thing that's interesting is this is a picture of radiosondes, and now we have the, let's see, where's my cursor? We see that the the height scale here goes from 5 to 25 kilometers. But right around here, there was a shift in instrumentation from a Cypicon Mark IIA to a Vizsla RS-92. So you see that, and you see that the fluctuations, so that the top figure is actually at 0 UTC and 12. You can see, and this would be sunlit. So you can see that both day and night, there's a discontinuity in the RMS features, the noise. So if you're looking at something where you're looking at the small scale features, you have to be very careful about this noise, and also it'll be different when you shift radiosonde instruments. And I forgot to mention, when I look globally, as you might imagine, if you look globally, there's quite a few different radiosonde instruments being used globally. So one of the things we'd propose, and I'll get back to that later, is to sort of a strategy using the same spline fitting and RMS would be to characterize the different instruments. And also, if you look at the raw and the process data, there's much less of a discontinuity, but it's still there. So this whatever smoothing they're doing does not diminishes this discontinuity, but it doesn't eliminate it. So this paper, the 25 JTEC paper, would be that there's greater small scale temperature fluctuations in the raw data than in the process data, greater in the stratosphere than in the troposphere, greater under daylit conditions, and perhaps due to uncorrected radiation effects due to radiosonde instrument motions. A discontinuity is seen in the small scale temperature fluctuations when there's a change in instrumentation. And I'm not getting into this later. I will talk about it later, but not quite now. Some of the temperature fluctuations are due to turbulence. You can't see that from anything I've showed yet, but hopefully I'll convince you of that in a few minutes. Okay? Now, I actually should go back a little bit. When in 24, 25, I was diagnosed to have a medical condition that needed a sort of intensive treatments, and I knew I was going to be tired and worn out from traveling to Tampa and getting all these treatments. And so I went on a writing, being the odd person I am, I went on a writing kick. So I was part of like 5 papers that I published. That's much more than I usually publish in a year. So the second paper I want to talk about is a paper in Monthly Weather Review that built on an earlier one in 2021. And here we looked at unstable layers. And by mean unstable layers, we're talking unstable layers where the potential temperature is decreasing over that layer. And we looked, and here we just calculated a statistic of the aggregate numbers, basically, of unstable layers of depth 10 to 400. Why we chose 10 to 400? Well, it's a reasonable range. But it was interesting what we found there. We found in Riverton, Wyoming, that these fluctuations were greater at 0 UTC than at 12, but at Greensboro, they were greater at 12 than at 0 UTC. So we had sort of a complete different situation at those 2 stations. Looking further, this is again the 21 paper. We mapped that out, and this is a crude continental US. So this would be Riverton, and this would be Greensboro. And you could see that there was sort of a day-night difference where if you went from zero, if you went from December, January, February for UTC, and here's 12, you see that these are consistent with what I showed you in the first one, but looking at the two stations, this is just a manifestation of this large scale pattern where in December, January, February, there was a smaller frequency, aggregate frequency in the eastern US, bigger in the western. But in September, October, November, it would be different. Okay? That's from the 2021 paper. So we wanted to see what was going on. So another feature of this 2021 paper, this is a scatter plot of, this is altitude, and this is the color scheme is the log of the frequency per sounding of the occurrences of unstable layers of thicknesses shown in the abscissa. And this is shown at Koror, which is in the deep tropics. This is 12 UTC, this is 0 UTC. And you see a curious feature. At around 12 kilometers, there appears to be a paucity of thin layers, but an excess of thick layers. And it occurs at an approximate altitude centered at around 12 kilometers. And because of the visual appearance of this, we refer to it as a notch in unstable layers. So two of the questions that arose in this 2021 paper is what caused that diurnal variation in unstable layers and what caused this notch. And we hypothesized that what caused that notch was, there's a paper from Grice et al. Where they used GPS soundings to look at the global picture of atmospheric stability. And you see at 12 kilometers, you see a stability minimum occurring at about an altitude of 12 kilometers in the deep tropics. So if you look closely, it wanders a little bit I'll show this in a minute, but basically you look at this, it looks like it's centered on an annual basis, plus or minus 15 degrees, say. Okay? But, so now we go to our 2024 paper, and in the 2021 paper, we analyzed raw data. And in the 2024 paper, we sort of answered the question, what if you use process data instead? So if you look at the thinner lines, you'll see the raw. If you look at the thicker lines, you'll see the processed. And you see this diurnal variation where it was bigger at Riverton at 00Z, and here it's bigger at 12Z. But if you go now to the process data, it practically goes away. It practically goes away. So we basically, that diurnal variation in unstable layers that we found in the 21 paper wasn't a physical effect. It was rather due to the day-night variation of the small scale features that were more prominent during daylit conditions than nighttime conditions in the radiosonde data, which manifested itself in this unstable layers. And again, these are unstable layers. This is in the stratosphere, I should have said that, and the same 10 to 400 meters thickness. And this is just the time series. of months since we began in there at Greensboro and there, well, there at Riverton and there at Greensboro. So that's what we found in the 2021 paper, but sorry, I did this badly. Um, if we go then, so here we show it. So badly went away. But one of the reviewers, every once in a while, reviewers come up with really good ideas. And one of the reviewers said, this is really curious because I would expect the unstable layers to always be greater in the process data than in the process data and in the raw data than in the process data because of the noise. But you see, at times, if you look at the red curves, the number of unstable layers is less in the process data, in the raw data, than in the process data. And so they brought up that question. And so thinking about it, we realized that Wilson had recommended a noise reduction. Given the noise in radiosonde data, when you look at the potential temperature inversions, the question is how much is due to instrument noise and how much is due to geophysical signal. So Wilson determined a way to do that. And what he basically did is he looked at the signal to noise in the signal in the trend versus the noise. And he rejected unstable layers where the noise was much greater than the signal. And what I mean by the trend is the temperature gradient with height, the temperature gradient with height. So we and everyone else who looks at this has applied these Wilson noise reduction. But if you think about it, the noise is greater in the raw data than the process data. We showed you that. So you will be rejecting thinner layers in the raw data than in the process data. So by rejecting them, you get less unstable layers at times. It's sort of anti-intuitive, but that we said in that paper is likely due to the noise rejection methodology of Wilson et al. And we show this in a couple of ways, but in this figure, we do it instead of looking 10 to 400 meters, we looked at 100 to 400 meters, and this effect went away. We always have greater unstable layers in the raw data than in the process data. So clearly this was occurring on the thin layers, 10 to 100, where there were greater rejections in the raw data than in the process data. I hope I made that somewhat clear. We can return to that if you want. The other feature is this notch I mentioned. So again, we look at the raw data and the process data at 12 and 0 UTC, and you see that the notch is still there. This is still Karor, is still there. But if you look a little more closely, if you look at 0 UTC, for example, in July, you see the notch is much more prominent in the thin layers here than here. And so this we also attribute to this Wilson business, because if we're looking at the trend, the signal to noise and the trend versus the noise, in this region, I showed this is a stability minimum in the Grice et al. So if it's a stability minimum, there's a small gradient. So the noise to the trend is going to be much greater in the stability minimum region because there's more or less a zero and near zero gradient to the potential temperature. And so you'll do more rejections. So we see this particularly during daytime. We don't see it during nighttime as much. But the notch is still there. But part of that notch is a artifice of the Wilson noise rejection methodology. Sorry, I'm getting quite technical here, but if you're ever going to use this data, you got to realize that. Again, if we look at in the paper, we found that there was this big discontinuity, okay? The discontinuity is much greater using the raw data than the process data. But if you look closely, it's still there. There's much greater difference between the 12 and 0 UTC after this time when we changed instrumentation than with the previous instrumentation. So, some conclusions from that paper is that the 0 to 12 UTC differences and unstable layer occurrences that were noted in the earlier paper are largely but not completely eliminated when process data are analyzed instead of raw data. The notch is still there when the process data and the discontinuity noted in the earlier paper is diminished when process data is used, but it's not eliminated. Again, if you're doing something that uses these fine scales features, it's something you should be aware of. So I mentioned this Grice paper, and he also has a figure in there where he breaks it down by season. And you see that this stability minimum, as you'd expect, migrates. If you look, for example, here in June, July, August, you'll see this minimum is, I've got the plus and minus, the 20 north, 20 south lines here. You see that you're grazing this in June, July, August, but you're not coming very close in March, April, May. So we looked at a couple of things. This is just exactly what we showed earlier from Karor, but now using process data. But now we also look at the stability, the average stability profile. And you see what I showed more or less in the Grice thing, that you've got the stability minimum over the same region during all seasons. We're in the deep tropics. And furthermore, it keeps jumping around when I'm not touching it. We can also look at histograms, and we'll see in many months there's a diminishing of if we look at, this is the notch region, this is below the notch region, above the notch region, we see the depletion of thin layers, and we see the excess of thicker layers, basically, in all these years. So that's at Karor. So we ask a question, is this true at all deep tropical stations? And it is. We look at Ponape, we look at Majuro, we look at Chuck, we look at Yap, all within 10 degrees of the equator, notches, low stability, paucity of thin unstable layers, more thick unstable layers. This is from a 2024 paper, Geller and Wong in Journal of Climate. So basically what we saw at Karor appears to be present at all the deep tropical stations. But we also looked at stations at the edge of the tropics. So San Juan is at 18.4. Remember I showed this this picture at 20, and you see there should be a seasonal variation of when this occurs. And we see this. We see in January there's no stability minimum at 12. It's actually lower down, it's not as deep. And here it's a little higher, but still not as deep. Now we're talking in July and October, there's a stability minimum at 12. And we see this notch. We don't see as much of a depletion here. And probably that's due to the fact that the the higher stability is due to a greater trend, so there's less noise rejection there. But we see also that clear when the stability is very low, we see a much more altitude confined enhancement than say here. If you look at the blue, you see it's over a much larger altitude region. So again, from this paper, we would conclude that that notch feature that was noted at Karor is present at all deep tropics stations analyzed. And that's consistent with the notch being associated with the stability minimum in the deep tropics at altitudes around 12 kilometers. And when the stations at slightly higher latitudes are analyzed, the stability, we see a coherent picture consistent with the annual change in location of the stability minimum. This just talks about the Wilson content. I should make a couple more comments. One is, what's going on at 12 kilometers? Well, 12 kilometers is roughly the altitude where you're blowing off the cloud tops. So at cloud tops, there's probably turbulence being produced at the cloud tops, and then that's being advected as you get the blow off the cloud tops. So that's what appears to be happening. The other thing at 12 kilometers is it's not uncommon for for aircraft flying from the northern southern hemisphere to be flying at those altitudes. So this turbulence or unstable region has been noted in aviation reports. Okay, last paper I'm going to talk about is I'm a co-author in this paper. Here I worked with a student at Yonsei University. And so he actually, I believe I showed you how more global high resolution radiosondes have recently become available. So he, together with, well, his advisor, Dr. Hae-Young Chun, me, and Bruce Ingleby at European Center, who's really been a key figure in making these data available. These data have always been available to, always been available to the operational agencies and organizations. And ECMWF has been key to pushing this buffer data, this high resolution data that they're using in their systems. But that hasn't been available to the research community until recently, where there's a European and there's a US NCAI making these available. So he analyzed a bunch of stations where the red stations have 1 second data. So that would correspond to 5 meter, given the rise velocity, the ascent velocity of balloons, about 5 meters resolution. And then there's the 2 second data, the blue, and then there's some stations for which both are available, the greens. So you see actually there's quite a global coverage. Obviously less in the oceans with radiosonde data. One might ask at this point, can you do this with GPS? GPS has good height resolution, but the good height resolution they're talking about is maybe a fraction of a kilometer. It's in no way competitive with the height resolution of these radiosondes. Now, he used the Thorpe method, and this was introduced in a Scottish lock by Thorpe, and it was adopted by Clayson and Kampfer. And basically what it does is if you have an unstable region, this is potential temperature, so this would be unstable where it's decreasing with altitude. And so you sort the sounding by moving mathematically air there. It would sort of correspond physically to overturning. And you do it every 5 kilometers. So these are all the displacements. And they sum to 0. And then when you look at the RMS of all these displacements, you get the Thorpe scale. And then the Thorpe scale is assumed to be proportional to the Osmondov scale. And then you use this formula from Kolmogorov theory to get epsilon, where epsilon is the dissipation rate of turbulent kinetic energy. So using the Thorpe method. Now I should point out, one of the things about the Thorpe method is you have to have the unstable region. And I'll talk about that a little later. Turbulence in an unstable region, you don't necessarily have turbulence yet. It might not have been initiated yet. That's one side of the coin. So it's not always associated with turbulence. But also, you have turbulence in stable regions also. So the Thorpe method has these deficiencies. Now, Ko and Haeyoung Chun are very close to the aviation community. So they took epsilon and if they multiply it by the thickness and divide by the thickness of the unstable region, they get this effective dissipation rate. And they plot this in these various regions. And so they, for example, because it's global, they can, for instance, say that the maximum they're seeing in the troposphere, first of all, there's more turbulence in the troposphere than in the stratosphere, troposphere. But for instance, it would be greatest in region 6, which would be the South Pacific in the troposphere, whereas it would be greatest in regions 5 and 8, Asia and Hawaii and South Africa in the stratosphere. So they're able to do this, but it's also all using the Thorpe methodology. Okay, so that's in the bulletin of the American Meteorological Society. I want to finish up by showing some figures from a proposal that I recently submitted to NSF that builds on our earlier research. And by the way, if anyone wants to follow up on this, you're free to, because last night I got a notice that this proposal was declined, which is depressing. That means I'm actually gonna retire. if, forcibly, because my research won't be supported. But I think there's some pretty good ideas, but you be the judge, okay? So again, this Thorpe method, there are two parts to the proposal. There's one part is when I showed you that there was a discontinuity in the small scale temperature fluctuations depending on different instrumentation, and I also showed you different instrumentations I used globally. The first part of the proposal is to characterize the noise characteristics of the different radiosonde instruments. And we proposed, for example, if our hypothesis is correct that it's associated with the movements of the radiosonde temperature sensor as it swings and rotates, then your RMS should follow the solar curve, roughly. So you could look at each station and stratify the RMS with the solar curve, solar radiation. And if our hypothesis is ready, they should be associated with one another. That's one. And then it should be different for different instruments. The other is to improve or at least give an alternative to the Thorpe method. And again, not only does a Thorpe method associate turbulence with unstable regions, but in much of the atmosphere, particularly in the stratosphere, you have wind shear serving Kelvin-Helmholtz instability. But as I explained, this procedure doesn't include wind at all. It doesn't include wind or wind shear at all. So these are some deficiencies of the Thorpe method. So I said that the small scale features could be associated with turbulence. This top panel shows the well-known quasi-biennial oscillation, where you have alternating easterlies and westerlies descending. Okay, so in this top, I've penciled in the red, which would be the shear zones separating easterlies to westerlies. The bottom is nighttime soundings, where we've plotted the RMS temperature fluctuations with the delta Z equals 100 meters, so the small scale fluctuations. And you see a definite signal of enhancements in these fluctuations that appear to be descending in the same manner. But if you look closely, there's a one-to-one correspondence between the descending shear zones and the enhanced RMS values, which are likely turbulence. So we conclude that these, and by the way, it's previously been shown that gravity waves will tend to break as they approach their critical levels. And so we would expect gravity wave breaking to be preferentially producing turbulence in these shear zones. And this, to our knowledge, is the first indication that we're seeing turbulence associated with the descending shear zones of the quasi-biennial oscillation. But here I'm just saying this shows that it's at least a qualitative. When we make it quantitative, well, this is a paper from Fritz et al., and where they did turbulence, very high resolution turbulence simulations, direct numerical simulations of turbulence at mesospheric inversion zones, a temperature inversion in a mesosphere. So you see the altitude region is much higher than you're used to dealing with, 70, 80 kilometers. So they put a shear zone, a mesospheric inversion, put gravity waves through it, and they got turbulence. The black curves show they can directly calculate the dissipation rate of turbulent kinetic energy. The red curves use this Weinstock formula, an empirical formula. If you take the fluctuations in vertical velocity, put it by a scaling factor and multiply by the Brunt-Weissler frequency, they're not exact, but they look quite similar, the altitude profile. Now, having said that, you have to realize these are a lot of profiles that are being averaged. So the averages are showing up. They didn't really, if you look at the next curve, it's basically the same thing for this one that goes 70 to 80. And these are the same curves I showed before, but these are all the individual determinations. And you see it's noisy, very noisy. But on the average, that Weinstock formula appears to work. And this is just the time scale they use and blah, blah, blah. Okay. Okay, so can we get the fluctuations in vertical velocity directly from radiosonde descent rates? An earlier student of mine, Ji Gong, used these ascent rates to look at gravity waves, but this is much finer scale, and it probably cannot be used because there's a lot of motions going on in radiosonde, the radiosonde sensor, and it's noisy. We looked at it and it just probably not. They probably can't do it. So then the question is, well, if there's fluctuations in vertical velocity, there should be fluctuations in temperature. Could we use that as a surrogate in the Weinstock formula? So here we look at for this simulation, this spheric inversion turbulence simulation, if we look at the averages of the fluctuations in vertical velocity and temperature, the profiles look rather similar. So we had proposed to see if we could use the fluctuations in temperature first to explore it within numerical simulations, and secondly, to actually look at it in instrumentation to see if we could actually use the temperature fluctuations that we determined from radiosondes as a surrogate for W's in the Weinstock. And that method would not assume unstable regions and would not explicitly exclude, it doesn't use the wind shear, but the Thorpe method uses the temperature profile but ignores the wind shear. This doesn't have that deficiency. But as I indicated earlier, although it got pretty good reviews, and all of them were very good reviews, this proposal was not funded. I'm afraid we don't live in great times. Anyhow, what I've done then is I've just shown some of my recent research involving turbulence from high resolution radiosonde data. And again, given recent NSF decision, I might really have to retire this time. And that finishes the talk. So I'll be glad to take any questions you have. Okay?
Great. Well, thank you very much, Marv. Very interesting. Yeah, so we have some time for questions. So
See if
anyone
I
want to
can
get us
figure out how to
started?
get back on get rid of stop share. There we go.
Okay.
Okay, there we go.
Any questions for Marv? Yeah, Minghua, you'll start us
Yes,
off.
hi, Marv. Congratulations for your true retirement and for your productive work in your semi-retirement. I have a question regarding the knots. That's interesting in low latitudes. I wonder whether it could be related with the source of the gravity waves because of convection. The depth is larger in the tropics, therefore you induce larger vertical wavelengths.
Yeah, I don't think it's, as I said, there are papers by Gettleman and there are papers by, I'm trying to remember the other one, Forrester. There are a couple of papers that associate this stability minimum with cloud top blow off. And the way I think of it, in convection, the cloud top's going like, it's sort of like you've got a stable stratosphere or stability, and you've got fluctuating cloud tops. It's kind of beating a drum, if you will. So you get I think turbulence at cloud tops. And I guess, Paul, as a pilot, you might confirm or deny that you'd like to avoid flying near cloud tops of convection because that's a region of high turbulence. And this turbulence gets advected. And I think that's probably what's going on at roughly that 12-kilometer region, rather than gravity waves per se.
Okay. Thank
Okay.
you.
I think.
Okay.
And by the way, enlarging on that, we didn't say at this 12 kilometers, we didn't stratify how much is taking place in clouds, how much is taking place in clear air. That would be another thing to look at. We have not done that.
Well, actually, that's what I was wondering. I mean, obviously at cloud top, there's radiative cooling, which can enhance or decrease the stability and lead to maybe some unstable layers too, right at cloud top.
Yeah,
Okay.
yeah.
Yeah.
And the unstable layers eventually would produce turbulence.
Yeah.
And talk to Dave Fritz, who's more of an expert in this than I am. These turbulence eddies can be fairly long-lived. They can be advected at significant distances. And again, Paul or some other pilot might comment on their experiences, but this, I believe, is the case.
Okay. Yeah. Jen?
Hi, so thanks for a very nice talk. It's eye-opening what you can do with sounding. So you part answered my question. You didn't look at whether you are in clouds or out of clouds, right? But do you have water vapor? So do you looking at a correlation of temperature anomaly with water vapor? That should be straightforward, right?
Yeah, I think we tried that a little bit, but we didn't find anything. It's water vapor at those altitudes from radiosondes is pretty dicey. Um, they're trying to improve the instrumentation, and I could be behind, but last I knew, water vapor measurements from radiosondes above, I don't know, 400 hectopascals, 300 hectopascals tend to be rather unreliable.
The Wizards are doing pretty good. So they after yeah. So another comment is that so the 12 kilometer probably is too low for a lot of tropical clouds, but ice crystal falling down from the cirrus clouds above could generating some interesting turbulence due to the evaporation. So
Yeah, I think your point is good there. The clouds we're talking about are probably not the hot tower type clouds. They're rather probably more the trade wind cumulus type of clouds, which are, I gather, I'm no expert in tropical meteorology, that I gather are the more persistent clouds, whereas the more dramatic ones would be the hot towers. But again, I'm just quoting the papers of Gettleman and Fuglestaller, that's the other one. Fuglestaller and Gettleman and Forster wrote these papers on the tropopause transition layer, and they point out that this stability minimum is associated with the cloud top blow off.
Yeah. Steve?
Yeah. Hi, Marv, and kind of happy to see another older guy still involved in this sort of research activity. It gets in your blood and you can't get rid of it. I don't know what you need NSF support for. You can just do it on your own anyway.
Me?
Yeah.
Okay. Yeah, okay.
What are the expenses? I don't know. But the you made reference to the fact that there's a proprietary algorithm to do the smoothing. And I would think that whoever's selling this product ought to be forthcoming with it, or you can wring their neck to get that algorithm or reverse engineer it. So I don't think I think you're spending an inordinate amount of time trying to do the comparisons and get rid of that proprietary difference that you might be able simply to eliminate otherwise.
Well, I don't want to get rid of it per se, because actually the smooth data appears to be have that positive consequences. But when you do smoothing, the ideal way to do smoothing would be to understand the geophysical signal that you're dealing with and make sure you're smoothing the noise, but not smoothing the geophysical signal. I don't believe that's the case. I believe that this is a crank that they're turning and looking at it. So they, but when I inquired, I did inquire from the Weather Service about the smoothing. They referred me to the Sterling Support Center that supports the National Weather Service radio sound operations. And I got an answer saying that the smoothing is proprietary to the manufacturer. I actually looked up the documentation, and the documentation on the smoothing was of no help whatsoever, perhaps due to the documentation and perhaps due to my limitations. But but yeah, I asked quite a few people to deal with the data more than I do, um, and they knew it was smoothed, but exactly how there are some obvious things. They're smoothing to get rid of some obvious noise features. They're obvious and they're well documented. But if you look at the plots that I showed of the early one of the raw and the processed, there's more going on there than just getting rid of bad stuff. There's a definite smoothing going on. And yet the smoothing improves things, but doesn't eliminate these day-night differences, the discontinuities. So actually in the reviews, some of the reviews said this is valuable to sort of the feedback to the radio songs people on their smoothing. And that was one of the motivations of looking at it for the different radio son types. So I think they should be examined, but we won't be examining it. Let me put it that way.
Okay. Yeah, one more question from Edmund.
Yep.
Are you there, Edmund?
Yeah, I'm there, but I'm struggling to move my mouse. So, uh, hi, Marv.
Hi.
Great to see you. Yeah, by the way, I was also hired when you were dean, so just
Right.
yeah. So it's very nice to see you again. So I have a question about what you showed in the early part of your talk that there's a striking difference, at least in the high resolution thing, when they actually change equipments. So does that actually impact sort of lower resolution stuff? Like how do the reanalysis actually handle those type of things? Because I guess not every station change at the same time. So you have one station change at one time, and then another station change at another time, and then there are discontinuities everywhere. So have you looked at reanalysis about what
No,
it
I
is?
haven't, but you brought up a very good point here, Edmund, as you do often, by the way. But the one point here is that ECMW has been a prime mover in pushing for the availability for the high resolution data, the buffer data for their operational work, their reanalysis, their forecasting, etc. If they find the high resolution data to be useful for these purposes, I would guess that problems in the high resolution data should be of interest to them.
Mhm.
Um, I don't know how, I doubt one of the wonderful things about reanalysis is that reanalysis can be used to look at data problems. In other words, if you get sudden departures between observations and analysis, there's a problem. I don't know if this has been looked at all. I haven't heard anything, but it's a good point. It's a very good point. If they're interested in high resolution data, they ought to know about problems and discontinuities occurring in this high resolution data.
Yes, I agree. So, anyhow, thank you very much, Marv. And let's give Marv another big round of applause here virtually. Thank you.
Yeah.
So that concludes our seminar. And yeah, thank you so much, Marv, for taking the time and yeah, I don't know. I don't know what to say. Best wishes. Part of me
Yeah.
says don't submit that proposal again. You never know.
I'll see what happens. We'll see what happens. I feel more as Steve sort of alluded to, it doesn't really affect me a hell of a lot. I mean, because you know, I was getting minimal support. All of the support was going to my collaborators as it should, because they're actually doing stuff. Um, but on the other hand, this was providing a fair amount of support to some of my collaborators, and I feel badly for them more than for me. It's as Steve indicated. I like doing research. It's my favorite hobby, but um, but it's a hobby. The other people, it puts bread on the table and pays the rent. It's different, you know.
Certainly. But anyhow, well, thank you, Marv, once again, and thank you everyone for joining us. And so anyhow, keep warm,
I,
everyone.
I hope that I will, though. You probably haven't seen the last of me. I hope to see you people
Yeah.
again.
Well,
Okay?
you're welcome to anytime, Marv. Anytime.
Okay. See you all.
Thank you.
Bye-bye.